the cooling section failure circuit, the first speaker is Professor Yang Yi from National University. He will tell us about the JSAC conducting proton and many other region stuff.
Thank you. So, as you realize, I'm probably the only one to talk about this experimental result in this meeting, the current session. So, but I really want to try to draw some attention to the series to this very interesting area, maybe to help us to predict more insight of physics of heavy collision. So, today my outline is I will give a very short introductions on the motivation in the star detector and read the heavy ion collider, and I will jump to two physics results on JSAC production in proton and photon collision, and I will summarize my talk in the end. You can see this is a beautiful star detector. Both theorists and experimentalists trying very hard to understand the production mechanism of the quantum, but still not very successful so far. So we have several popular models in the market, like current singlet, current octet, current configuration model, but none of them can describe its production cross-section very well. Like for example, it's the CDF result on Wolfstone 1S. So you can see it's the measurement, but if you only consider the linear order current singlet model, it's clearly underestimated. You have to input some contribution from the current octet mechanism and fit data pretty well in the heavy region. This region, they have some theoretical issues here, but normally we need to add some contribution in the model. So furthermore, if we study the quantum, if you look at the production rate in proton collision or in the heavy ion collision, you compare the production rate, you can see there's a strong subtraction in the quantum system. Then this will give us a hint on the give us some information on property of quantum dynamics or the quantum task of QGP. So these are our main topics on studying these heavy ion collisions. Some basic information on QGP is it's a new phase of the matter. It's very high temperature, very high chemical energy, so about 4 times 10 to the 12 Celsius. And in this state, the quark and gluon are free states. They are no longer confined. Interestingly, we find this behavior, the quark to gluon system, looks like a fluid, not a gas. So it has moved in the correct directions, and also it can describe the behavior by the hydrodynamic equation. We assume the viscosity and the entropy density ratio is pretty small, so we can describe this system pretty well, and also it has the direct distribution of the thermal energies. Very, very perfect fluid-like system. But in this system, the lifetime is very short. It's less than 10 to minus 21 seconds. This will create and finish very soon. In this system also, the color charge will be screened because there's so many other charge color particles moving around in this system. So basically, it's like a soup of the quark and the free quark and free gluons. And how to study the QGP? So one way is you can study the jet function, or the other way is you can use some probe like the JSAC Quantum system to study the QGP. So when we see the suppression of the JSAC production, is a very clear evidence of the QGP formation. So because if you have a medium have a very many free quark and gluons, JSAC will melt it and it will regenerate in this system. So the production rate will decrease. But it's very complicated to clearly or correctly interpret this phenomena because there are so many effects can give you very similar results, like the hot nuclear methods, cold nuclear method, or you need to understand the feed down from the excited stramonium and or the B cathode. So here to show the one of the theoretical calculations, you can see there's many different theories can predict the contribution, and you need to really add them together, or you need to find the correct ratio to describe our result. So we did this experiment. We can do it in the Large Hadron Collider, or we can do it in the relatively heavy ion collider in Blue Heaven National Lab. So it's in the Long Island. It's a very nice heavy ion collider. You can see there's actually it's only two major experiments so far. It's STAR and the Phoenix. In this collider, we can collide the proton-proton particles, proton gold and e-gold, gold or uranium. So depending on what physics you want to learn, so you can change your input particles in the ring. And also we can also keep the polarize on the proton, so we can study the polarization of the proton particle. So here to show the main side of the Blue Heaven National Lab. So, National University is working on this experiment. So here to show the star detector, we have so many, we have many parts. Like the normal particle detector, we have the inner tracker, the HFT, and we have the outside is the time construction chamber. It can precisely measure the momentum and the EDX for particles. Covered region for eta is the pseudo rapidity less than 1. Outside the top, we have the time of flight. We can do the particle identification. We can measure this the electron or pion or photon or some other particles. And also outside top, inside the top is the BEMC, the barrel electromagnetic calorimeters can trigger effects, or we can measure the electromagnetic energy very precise. So and also can do the particle identifications. We also have a newly installed detector we call neon telescope detector outside the star detector. So with this detector we can measure the neon effect. Very nice, simple detector we added in 2014. So now let me jump to some physics results. So first, we are using proton-proton collision at 200 GeV collisions, and using the J-side phase to that electron channel, the total velocity is about 25 g/pound, and we have very basic candidate selections. So you can see a very nice J-side peak around 3.1. And also we use the data from proton-proton collision at 500 GeV, so we double the collision energy. You can see a nice peak in J-side, and we can also see the side-to-side state in this region as well. With the newly installed detector in 2014, we can look at the J-side decay to dimuon channel. So this is the dimuon mass spectrum in 2013 mode. In this year, we only installed half of this detector, so in the future we have much more data. In this analysis, we only apply very, very simple concepts, so we don't want to bias our events, so we just apply a simple magnetic flux on mu or electron candidates. So we measure the J-side cross-section in the dielectron channel, 200 GeV proton collision, then we compare with data. You can see it's the condensate model plus the non-relativity QCD can describe data pretty well in this region, but not in the low PT region, because we only estimate the production rate a little bit. And high PT region, we can use the next leading order plus the QCD model to describe it well. On the other hand, we can use the Howard effect integration model plus the QCD. That's what we forgot to mention here. Discuss the data very well, but none of them can singly describe the measurement correctly. Similarly, we did this measurement in J-side decay in PT at 500 GeV. So So this measurement from electron is a red line and red dot. From electron is compared to the next reading order NR50B. It's pretty good, but it's pretty problem in the high region. And also we compare to the dimuon channel result with the powder condensate model. Also, it's a little bit similar discrepancy in the very low region. So again, so we confirm there's no good single model can type this component production very well. And also we look at this XT scaling, so basically it's the PT over the collision energies. This like very linearly, but it's a little bit breaking down in the low XT region, so it might give some soft protest events. And in 2011 data, because we have a nice peak of J psi and the small peak of ZQS, and we can do this ratio for free. We just calculate the ratio of these two candidates. So we find this very similar results the other experiments, and we find there's no collision energy dependence on this ZQS to J psi ratio. So this is from the era A and era B in electron dimuon channel, and this is from Phoenix. This energy, and also this triangle is the CDF at very high energy, 1.8 eV. So you can see this trend is no collision energy dependence on these ratios. So it gives us very universal property of these two particles. Then also we can look at a very interesting quantities, the J psi EL versus the event activity. So we look at the J psi production and count how many charged particles around this event. So that's what we call event activities. So you can see there's a very nice trend, looks like increasing faster than the linear function. So we don't know what's going on, but it's described by PCR simulation and this configuration model quite well. So we still try to understand what's going on. And this, you can see there's a result from Alice on the D meson and the start on the J psi. They have very similar behavior. So there's so many questions in the component system we need to understand. Now it goes to the J psi to mu in GoGo collision in 200 GeV. Similarly, we have, because in the GoGo collision, we have much more background. So you can see the raw dimuon mass spectrum is very blurry. So you cannot clearly see the J psi signal. If you do the subtraction of the background, you can see some J psi peaks here. So we probably want to need some advanced selection on the muon identification in the future. That will be our next step. But in this data set, we already can do very nice basic result. So first, we can do the event EL. So we either correct the if we didn't correct efficiency, didn't correct the acceptance, didn't correct the luminosity, we just look at the EL of the J psi. You can see it's described by this model very nicely, and our new detector can measure this result consistent with the diagonal channel very well. And now goes to a very important result in the GoGo collisions. So we compare the production rate in proton-proton and in heavy-ion collision. So the RAA means these quantities. It's the number of J psi in the GoGo collision divided by the cross-section in PP collisions, and we divide by the common factor. TAA is the average collision particle divided by the in electrics PP collision section. So this result shows the centrality. Centrality means how particles collide. So in the heavy ion collision, you have two gold ions. It's pretty long. So you can have this central collision or this head-to-head. It's like 20% collide. So in this 0 to 20% means it's collide to head-to-head. So you have much more event around the system. And so we don't see in this collision have a strong peak-dependent subtraction, but we do see a huge subtraction in the GoGo system. But in this kind of collisions is only some overlap for the two gold particles you can see there's a racing trend. The RAA is variable. It's increasing increasing with PT. So this might due to the cold nuclear matter effects or some generation effect. Similarly for these very far collision candidates. But as I said, if we want to explain this result, we need to very carefully consider all of these sources, like the dissociation, the cold nuclear matter effect, the formation time, or the dihedron theta contribution. Also, we can compare the result with this we call the multiplicity. So it's the look at how many charged particles around the event. So we compare our result with the measurement from LHC. So they have much higher energies around 2 TeV. That collision. We compare the result with the PT, inclusive JSI PT, which means PT that greater than 0 GeV. We can see the LHC result have less suppression in the active region. So that means maybe in this energy, they generate much more free trunk parts. So they have more chance to be combined to form a J-side particle. So in this region, they increase the J-side, the RA value in the active region. And if we look at the effect only J-side PT greater than 5 GeV, then you can see much suppression in LHC effect. So we also compare this measurement with some theoretical models, but none of them can describe very well. Like if we consider this dissociation and general effect in this transport model, you can see this is the start data. This looks fine, but this model cannot describe LHC data very well, which means we probably miss some important insight on this Coulomb plasma event. And also, if you look at the high PT event, this is the LHC data. It cannot be described by this model. So this model has a very strange behavior. So finally, as I mentioned in the beginning, though, so this Coulomb plasma will give we call flow, just looks like the perfect fluid in the system. So maybe JSI will look at in this way. So how do we test this idea? So we can look at production in the azimuthal angle. We can do this kind of the Fourier extension. We can have this many terms. It's a second term on the cosine and the fourth term on the cosine transform. So this means the V2. If we calculate the effect distribution according to this formula, we can extract this V2 lenses. So there are two main production ways of the J side. You can have the primordial production, so it's basically 0 V2. It looks like it goes all the way in all directions. Also, if we generate event, we can inherit the V2 from the trunk box. So this is our first result. We measure this J-side V2 from diagonal channels. It's very consistent with our result from electron channel. And you can see clearly after a certain PT region is close to 0. But our uncertainty is still large, so we need more data on these measurements. So we really need some input from series to help us to understand more on these Coulomb plasma events. So let me summarize on my talk. So we have a new installed MDT detector. So this allows us to study diurnal events in star. This can reach to 0 PT kinematic region. This can give us much more information on this QGP. I also show the J-side production in PP at 12 GeV and 51 GeV. Shows the double differential projection. Looks probably okay compared to the theoretical model. Also, I show the ratio of the centric to J-side and look at the J-side EL for this charged particle multiplicity. And in the end, I will also show some results on the total collision point of view. So, thanks.
How do you measure the centrality of information in the?
So basically, you measure how many charged particles in the event. So we just define in this diagram. You can look at what's the probability happening with this kind of this event.
Page 17, you have this ET spectra, and we pointed out this discrepancy at high ET. So are radiative corrections included in these models?
Which
So
correction?
hard lower emission.
Oh, in this model, I'm not sure in this model. I think they only include the dissociation and diffusion.
Because that usually hardens the spectrum.
That's a good idea.
Because the discrepancy is not so big.
Right.
Right.
But error bar is yeah. If you look at the central values. But I think the most important match from here is the result from LC and the star. Different energy, we have very different
Yes.
RA independent RA.
And then on the right, we have an idea what is, one
Sure.
model is very smooth, the other has certain things.
I
should be reasons for that.
I know. I think they tune some parameter in their model because they have each of model have two types. Maybe this one is the general model and the other one is they have some parameter they can tune. That's my guess. But still, if you tune, you can fit this point well where you look.
Okay. Any other? No, thanks, speaker. Okay.